where I left off in the first part of my presentation, I was talking about this double helix ghost number cube and its one state. That means that no matter where you rotate it around, either which way, any axis, anywhere, it's only going to have one state of the cubic octrants that preserve the 1/3. And this is all in addition form. Preserves of 1/3. They're all universal. This is universal as it rotates around 36, 36, 36, 36. The 18 is universal in here. The ghost number, or the central cube, ghost number 12, is universal, and it's always. And the second inner ghost number cube, these inner ghost numbers represent the complementary aspects of the basic four observables. I guess in a deterministic cube it would be unobservables. I guess that's just my imagination, but and this redundant part would of course be the same because it's the same as this. The redundant part, it doesn't need to be included because it's the same. But in the full sense, the double helix ghost number cube is always going to be the same. It's a deterministic cube, and all this is commutative. Indeterministic cube, where this represents just one state, but it's one state out of universal, unique, universal, unique, and the redundant part would be universal again. Central ghost number is universal, and the outer ghost numbers are universal. But the purple inner parts that represent the weight, I guess, of the unobservables, or the observables in this sense, the indeterminacy, commutative. These are all commutative. The whole thing is built on the commutative property. These are commutative matrices versus Heisenberg's non-commutative matrix mechanics. These are commutative. It's built on the commutative property. 3 on this side, 3 on this side. I just have my speculations about where did you get the 6 numbers from? Are they is that the full 6 basic properties of the quantum world? Angular momentum and stuff like that, I guess. Or are they something else? I'm not really sure. But this is a typical magic ghost number cube, 4 states. This only shows one state. You rotate it around, you'll get the other states. 12. From 12 down to 24 is what I'm showing here. But you can turn it around and show 15 down to 21. 21 down to 15. Those are 2 inverse states. That's something to consider. Of complementarity observables. And then you go back to, here's 18 and 18. Those are equal states. Those are equal chances of happening, just like over here. They're all 2 states, equal 2 states, equal chances of happening. I think equal probability weighted is what I think these spatial-diagonals represent. Once again, these are all universal. This is my deterministic one state. Deterministic cubic octant ghost numbers. And these are the typical magic ghost number cube, 4 states at the most. And they can range from 2 states to 3 states to 4 states because there's 4 different spatial diagonals. So there's 4 basic states of these observables, complementary observables. These are what I guess must be the complementary unobservables because they're all deterministic 18. They're all 18, 18, 18, 18. And there's a lot more to be discovered and a lot more for me to learn about quantum mechanics to apply these pure mathematical ideas to me. They're pure mathematics. I'm not sure if somebody's already discovered them and they're trivial to high schoolers or something. But they're really interesting to me, and I'm always trying to apply them to complete a full quantum mechanical matrix mechanics. This is my contribution, my deterministic one state. Also captured in my commutative ghost number cube, magic ghost number cubes, the indeterminacy of the observables of Heisenberg's states. So this is it's art, I guess. It's storytelling or something, mathematical storytelling. I can't really claim to be any truthful about this than anything else, but this is what interests me, and these are something I'm trying to build on. This is my contribution, double helix ghost number cube, because it's 1, 2, 3, and 1, 2, 3. You can go 4, 5, 6 or 4, 5, 6 down here. It forms a double helix of numbers going around the cube, back to front, or I guess you can have front to back, but it's 1, 2, 3, and it produces 3, 4, 5. 1, 2, 3, 3, 4, 5. A lot of symmetry around this cube. And not so much symmetry around this cube. Not too much symmetry, but there is symmetry. There's an 18 and an 18. There's a 21, 15. There's a 21 down here in the 15. And there's a lone 12.